probability. Before I get into that, I was going to do section 3.2. Any questions at all? Blake, you sent me something. I'll provide, if you want a Gaussian formula or Rayleigh, I'll put it on the board. All right? I didn't worry about that. What do you got for me? I just saw that on the way in.
Yeah. 3, 2, 1.
Yeah, okay. So this is conditional probability. How about before I talk about 3, 2, 1, I do a little theory? Because I hope, how many read this, section 3.2? All right, now, conditional probability. The real problem with this is understanding how to think of it in terms of the area ratios. I like to think of it that way. So if you have an event space like so, this is a little theory. I'm not going to go through the whole lot. And this is event A, and this is event B. Now this is going to be total probabilities, right? And we want the event that given B, A happens. Now this is pretty straightforward. This is this crossheads theory. So the probability that A will occur given B has occurred is really the probability of A intersect B, and that's represented by that cross-hatched area. This goes back some time, right? And it's divided by the probability of B. So that's a simple way of thinking about it. Okay. Now, what he does, he likes X and Y. He doesn't like A and B. So if you take a look, and I'm trying to do this the way, according to his book, and he's going to say this. If we talk about two events, and I'm going to use X and Y as the event spaces, and they can be either conditional or unconditional. They can depend on each other, dependent or independent. Right? So in his book, he says, let me get rid of this, because you notice this. I'm just putting this up here as a starting point. And this is the probability, I don't even know if this is in his book or not, of A greater than or equal to, this is a random variable X less than or equal to B, and then intersecting, I'm going to go back here first for a second. Yeah, intersecting that C is greater than or equal to Y, less than or equal to D, and as such, and here, let me change this, make this X, make this Y. I'm doing this for a reason, so you can see what this really is going to say is now instead of having an overlapped area as such, it's limiting the values of X to be a certain range and Y to be a certain range. This would be like a square area or a rectangular area. Y'all follow me on this, class? I'm just showing you this. So what is this, first of all, in terms of the density functions? This is pretty straightforward, and I'm doing this where these limits have nothing to do with the value of X. If it was an oval, it would change. Do y'all follow me? Or a circle? I'm trying to make it simple here. So this is just f of x, y, dx, dy. Here, x goes from A to B, and y goes from C to D, and that's straightforward. And if I looked at this, I don't even know if this is in the book or if I got this somewhere else, but if I look at this and I talk about this being X and this being Y, then you would see this kind of a deal. I think this is in Bonston, but I'm not sure in chapter 8. You can check me if you want. And what we're really saying here is it would be represented, it would be associated with that area shaded right there. If that's X and Y, and these are random variables. And that's the event space. Now, for this one, I'll tell you why I'm doing this, because some of this stuff will overlay perfectly, I think. It'll make sense, a lot more sense, at least than what I saw in his book, in section 3-2 in our book. So if you think about this, and we write it in terms of a conditional density, an unconditional density function. Remember, when we talk about f of x comma y, now this is going to be the distribution function. That's a double integral from minus infinity, x minus infinity, or I can put y out here. No, I guess x, y, of f of x, y. And then here, it's going to be dy dx. So that is what this indicates, right? It's always an integration from minus infinity to the point x of the densities function. This is a joint density. You all with me, class? Just want to make sure. I'm not trying to do something here that is out of bounds, but I'm trying to show you the distribution function relationship to this concept, so hopefully we can move forward. So what is this going to be? Now think about the areas. First, if I take f, and I'm going to take the outer point here, which is going to be x is b, y is d. So I have f of b comma d. Now what is that? Well, that's the probability of this area right here. Can you all see that? You all with me, class? It's everything in blue. So if I start there, now we have to subtract off areas if I want just this black cross-hatched area. The first area I'm going to subtract is this area down here, this lower quadrant. So let me see if I can push this in purple. You'll see what I'm doing, I think. So that would be f of, and it would be x is b, but y equals c. Do you agree with that? So I take minus f of b comma c, and now I'm going to subtract off this area right here. What I'm trying to show you is this. So that's going to be minus f of, and here, x is going to be a, and y is going to be d. Now, what happened is I subtracted off this area twice. Can you all see this, class? So I have to add it. So it's going to be plus f of, and here it's going to be x is a, and y is c. And that would be, this would be the actual distribution function you could use to get this, because the bounds are not dependent on one another. Like, it's not an oval region, it's rectangular. Does everybody follow me on this, class? In his book, he shows a lot of distribution functions, and he has a lot of things before he takes a derivative of them. Y'all follow me? And this is for two random variables. The probability of x, and do I want to, yeah, I'm going to do random variable x being greater than or equal to a, less than or equal to b. Better yet, let me do it this way. Yeah, I'll say this. Given that y, random variable y, is between c and d. Well, now for this one, if you think about it, we want this based on this condition. So I'm going to try to draw a Venn diagram. Let's hope I get this right. So here's x, and here's y, and here's the adjoining areas. And I say y is between c and d. This is where it gets a little hard. So where is that area? Well, it could be in here. Can you follow me? If y, for instance, if this, and maybe I should do it x, y this way, but these are two events, and it's hard to draw this. So if we say that the event y is here, if that occurs, you can see the probability of x would just be really, if they give you that this event occurred, it would be this area, and then you would have to divide, you would have to take that area, and first you'd have to take this dark blue, purple area here on top and divide it by this area over the sliver. I'm trying to show you that, right? But if y was down here, if this is where the range was, then if this occurs, x doesn't occur. Do y'all follow me? I mean, the two have no, if this occurs, if it's given this occurs, this can't occur because there's no overlap. That's what I'm trying to show you. Yes, sir.
So X is dependent on Y, pretty much?
Well, the way, I want to say this, what I'm showing you is the overlapping areas. And you can see x and y would be dependent here, right? I mean, if y occurred, the probability of x occurring is limited. They're not disjoint. Y'all with me on this? Yes, sir.
So in this case,
I'm
if
not
you're
saying
talking
this.
about the probability A less than X less than B, given Y occurring, and Y is that little area, it would be
Yeah,
0.
Yeah, right. And the problem, this is what I'm trying to get at. The problem with this kind of notation here is if it's rectangular, it's easy. I mean, if you just have, but if it's not, it's very hard to state this simply in terms of the density functions without putting the integrations down.
Yeah.
And then the limits of one depend on the other. And like when it's a rectangular area, it's straightforward. But if it's a circle or an oval or something like that, or a triangle, then it gets crazy. That's what I'm trying to indicate here. There's certain things he didn't state explicitly in that section that should be stated in the examples. I'm going to give you a couple examples that will make it a little more clear, I think. So next, so if I have this kind of an oval here, and call this the x dimension, and y. So now what I'm going to take a look at is, and I got to make sure I get this dependency the way I should state it. This is an event space that can happen. So if I take a dx here, and maybe this should make sense. Call this dx thick right here, or delta x. You with me? Matter of fact, I'm going to call it delta x. And I say, and again, we're going to have this represent some f of x, y. I mean, inside here, there's going to be a f of x, y, a two-dimensional probability density function in this area. You all follow me in this class? I'm just trying to give you an idea. So if I say that I have a given value of y that occurred, or dy, and there's two ways to do this. You can have an actual value of y or a differential value of dy. Yeah, I'm going to say a singular value first of all. So this has an actual thickness dx, but this has a value of y. So we're saying this is what I'm after. If y does occur, right, then what is the actual value of the probability of x? I call this x here, so it'd be of x greater than, maybe I should do it this way, of x minus delta x over 2 greater than x, random variable x, less than or equal to x plus delta x over 2, given that y equals y. I mean, random variable y equals y. All right, so I know this language isn't good, but I'm saying I want to know the probability if this occurs of this occurring, the density. You all with me, class? The density function. So the idea is, he says if I take f of x, y, and here I multiply that times dx. Now that's this purple area that I try to hash out. By the way, this is in the book Bonsolet. This drawing, it's the book, you might want to write this down. It is on page 197, so you can see where I'm getting this. It's a little better, in my opinion, it gives a better idea of what's going on. They want, so that's that area, but it's given y equals y, right? So, given that y equals y, here is going to be fy of y, and that is equal to the actual density function f of x given y right here. Remember, he says y occurs, right? But I'm really saying this occurs, this happens, so this is a thin line. I mean, it's an infinitesimally thin line, you might say. This is a differential, dx, but we want to know what is the probability of delta x occurring, or of f of x, the probability of this event happening when it has an area or with a width of dx at a value with a value of y here, given y occurred. So I have to take f of xy dx, that's this whole thing, and then I have to divide it by this differential area there. But that would be equal to f of xy dx. And what's going to end up happening, I wish I could say this better, and I'm not. This is what's going to happen. You're going to find that f of x given y is equal to, and this is in his book, f of xy over f of y. Now, the way in other books and stuff that they actually show this, the conditional probabilities like this, where it's given it occurred, they'll show something where they'll have a two-dimensional f of xy here. And they'll put an xy down here. Then they're going to say that if something occurs, if this is the x direction and this is the y direction here, if I give you that a certain value of y or range of y occurs, then over this f of xy region right there, if it does occur, this is the area you have to worry about that you're going to divide the actual divide by. It'll be in the denominator. With me on this, class? Then you have to find the intersecting area. Here's f of xy. I'm saying that this event y occurred, so this happened. That event happened. What is the probability of that happening, or the density function associated with that? Now you do it this differentially, so you take it. This would be a dy here, thickness, and this would be the entire span, so it'd be integrated over dx. And the way it's represented is, when you take a look at this, if you take f of xy here, and you're going to do it dy in this case, I'm sorry, dx and dy. Then you're going to take f of y dy here, and this is going to be an integral of f of x given y, and it's dx dy. No, it's just dx, that's right. Then this cancels that cancels that, and you should get that, and that is in his book if you look at this. What he's going to have is this, that f of x given y occurs is equal to f of x comma y. We're going to do this one, and hopefully I start making sense, because I'm not doing justice to this, and I know it, but I'm trying my best. That's what's going to come out of it. And actually, it's his base theorem if you actually get down to it. That also means that f of xy is equal to f of y of y. And the way you get f of y or f of x, regardless if it's dependent or independent, is integrate f of xy, integrate the value that you don't want out. If you have an f of xy and you want an f of y, you integrate dx, technically you have to put a dx prime and an x prime, integrate it from minus infinity to infinity to get dy. Can you follow me on this, class? But it's always ratios of areas to me. And this is going to be equal to f of y times f of x given y. And likewise, if I have f of x, y, is equal to, right here, f of x times f of y given x. The two, and basically if you just equate this to this, you get base there, differentially. That's what happened. I'm not pleased with the way I'm explaining this.
Single x has a Rayleigh density function and mean value of 10.
But it has a mean value?
Of 10.
Okay, so that's x Rayleigh equals 10. Okay, go ahead.
And is added to noise n that is uniformly distributed with a mean value of 0 and a variance of 1.
So we got noise x. That's got it. All right, so average value of this is 0.
And
Wait, the noise is an x. The noise is n. I think, right?
Yeah.
Yes.
So this is like Gaussian noise, but this is, I think, is it uniformly distributed in the cell?
Yes.
Okay.
And the variance is 12.
Okay, so sigma of the noise is 12, and now,
X and N are statistically independent and can be observed only as y equals x plus h.
this is a weird one, but it's actually very appropriate. So they're saying y is a variable, and it's equal to the actual signal you want plus the noise. Let me tell you where this happens. If you think about a channel where you've got information going down, the signal is sent assumed pristine, and you know the statistical information about the signal. Then on the receiving end, there's noise in the channel, usually Gaussian noise or something like that, something very definable because it's usually a naturally occurring event. So we get this. Now what we'd like to do, and this is something you get in at the higher level communication stuff, information theory. Have you had random yet?
Random?
I mean, have you had communications yet? I'm thinking of Jitendra's, his higher level random course. Jitendra teaches COM and he teaches a course in information theory that's really random communication stuff. If you think about his stuff, it's always involving real world noise and the ability to pull signal from noise. And there's something you're going to learn about coherence in this later on. So we'd like to know, if we get this, what confidence do we have that it's the actual value of x? That's what we really want. So go ahead and ask the question. Oh,
Find, sketch, and label the conditional probability density function f of x given y as a function of x or y equals 0, 6, and 12.
this is a great problem. I want to show you. So first, over here with the noise, I don't know if you remember this, but when we have something where we have, it says the noise is uniformly distributed, right? All right. So it's going to go from some lower bound to some upper bound, and it's got to have a value here that has a value of 1 over 2a. It has to, right? Because the area under that, this would be for f of noise. F of n, and this would be the noise value. Okay. I'm just trying to show you this in the simplest possible terms. If you look at that, if we get the standard deviation, standard deviation because it's 0 mean, then the actual mean squared value, because this has a 0 mean, would be the actual sigma value, that sigma squared, the variance, right? And if you look this up, we could do it. It's going to be, I think that sigma squared over 12, I'm trying to think about this. For this one, we can do it, but if he gives this a value of 12, so I know that's a constant value, and if I want the value of sigma n squared, because it is equal to the actual value of n squared, I mean that value, because it's the mean squared value because it's 0 mean here, then I can simply take the integral, 2 times the integral from 0 to the upper limit, which I'm calling a, of the sigma squared, and I'll call it n squared, right? And then times the density function, which is 1 over 2a, right? I integrate that dn, and that should be my sigma n squared. Let's see what we get here. We got 1 over a, right? And then I integrate n squared, so it's going to be n cubed over 3 from 0 to a. And what is that going to be? That's going to be 1 over a cubed over 3 equals sigma n squared that he gives us. Is sigma n squared 12?
Yes.
All right, so if that's 12, that's equal to a squared over 3, so that's 36 is equal to a squared, or a is plus or minus 6. And that's, so this should be minus 6, and this is plus 6, if that's the right definition. If you get that right here, now we know what f of n is, and f of n is simply going to be equal to 1/12, right? because it's 1 over 2a, and this is only going to be for minus 6 greater than n less than 6 and 0 else, so I just put it this way. And now we have to write the, we have to use, what was the Rayleigh value? Well, sigma Rayleigh is 10. Now, the problem is that this is a mean value with the Rayleigh, but with the Rayleigh distribution, you remember they have two Gaussian distributions that both have 0 mean, x and y, that create the Rayleigh. This is actually given as the square root of pi over 2, and that's sigma, but this is sigma Gaussian, so I always put a G there or something to indicate it is the Gaussian sigma. Y'all remember this? Now, I would give you this information. This would be unfair. So, this is, so that means sigma Gaussian for the Rayleigh is going to be equal to, so I have that, and then for the Rayleigh distribution, I have f of x, because x is Rayleigh distributed, so it's going to be x over sigma squared, but it's sigma Gaussian, it's that sigma squared, and it's exp to the minus x squared over 2 sigma Gaussian squared, and that's going to be for x greater than or equal to 0, less than or equal to infinity, and 0 else, right? Now he asked for, you gotta tell me exactly what he asked for. He wants f of x, right? Given we know what y is?
Yes.
All right, in other words, we know what the signal is we receive. We would like to know something about the density function of x, all right? That way we can figure out, if we have the f of xy, and we want to know the probability the signal is correct, we can integrate over the range of values that we have. More on this later, but I think you can appreciate this is an important piece of information. Now, what technically this is f of xy, that I'll get to in a second, divided by, and this is going to be f of y, based on Bayes' theorem and stuff like this. Okay. The whole trick on this one is this f of xy, you can replace, I'll put f of y down here, f of xy here can be given, if you remember, this is f of x given y, but f of equal to what? F of xy, same on top, but on the bottom, f of x given x. Do you remember this? So I can say that f of x, I don't want to mislead you. I looked at this last night. I don't remember. I even looked at it a little this morning. But this type of a problem, you have to be clear thinking about the relationship of y. Y is equal to x plus n. We know the densities of both of those. So if x is given, we can get the density of y. Or I should say, if you want the density of the noise, you could replace the noise with y minus x is basically it. We can get the density of y given x in this one. So we can see f of xy for this one is going to be f of y given x times f of x of x. And this is the key. So I'm going to take this and put it in here, and then I'm going to start just, you asked about this one, so it's an interesting problem. And then I'm going to replace this with some of the information over there. So that is f of y given x times f of x of x. And that's, that is f of xy, right? Now, going back to this. When we have f of y given x, here's the deal on this one. Y, not random variable, actual variable, equals x plus the value of noise. Therefore, if x is given right here, I can say, or basically I have y minus x is the noise. This is the key to this whole problem, in my opinion. Y'all with me? If x is given, then y and the noise, y minus x can be equated to the noise, And we have the distribution for the noise function, right? So we can say that this, or I can say that, sorry, f of y given x is simply going to be f of the noise of y minus x. Because we know x, right? We have the density function for the noise, we have the relationships of these things, so I can say the noise itself, if we have that density function, we do, I can go ahead and just replace the n with y minus x. And I think he does it this way in the book, but I don't remember exactly. The whole idea is use that information to get f of x, y without actually writing down something that you don't know. So I come up here, and when I do it, I'm going to have f of y given x is f of the noise of y minus x, and I'm not going to put that in there yet, times f of x of x over f of y. Now we just have to do some basic stuff over here. So now I need to go ahead and solve for f of y. I have f of x. I've got f of x right here. And now I need and I've got my f of y given x. Erase this, I'll put it right here. F of y given x is equal to f of n of y minus x right here. And let's see, now I need f of y. So to get fy of y here, I'm going to go ahead and integrate from minus infinity to infinity f of x prime y dx prime. And that's really going to be the integral. And f of xy is the thing I put right, is f of y given x. And that's this. And I guess I can put this in here. So this is going to be 1/12, right? And then it's going to be y minus x. Excuse me. It's 1/12, pardon me. I got to put the limits on here in a second. I'm putting this in here, and I've got to make it, the limits are going to be determined in a second. So that's f of y given x times f of x, and then f of x is that one, so it's times x over sigma Gaussian squared exp to the minus x squared over 2 sigma Gaussian squared. And this has to be integrated. You got to integrate out dx. Actually, it's technically dx prime over the limits. And this is going to be from y minus x equals 0 to y minus x, or sorry, not 0, minus 6, pardon me. Minus 6 to 6 right here. Y'all follow me on this, class? And the way he does it, since it's a dx prime, so this is going to be, here it's going to be x prime equals 6 plus y, and this is going to be minus y. If you think y minus x is equal to 6, right? That means x, take that over here, is y minus 6, right? Oh, y minus 6, sorry, y minus 6. And this is y minus 6, my bad. And this should be y plus 6. That would be the range. So then this one should become, and you tell me if I'm wrong here, but for this one it should become 1/12. And then I'm going to take the upper limit, so it's going to be, this is going to be the Rayleigh distribution of 1 minus exp to the minus y plus 6 squared over 2 sigma Gaussian squared. Now that's what I'm trying to do there, is just show you that that would be the Rayleigh distribution function evaluated at the upper bound, and then I'm gonna subtract off the Rayleigh distribution function at the lower bound. So it's minus quantity 1 minus exp to the minus y minus 6 squared over 2 sigma Gaussian squared. And that itself, you're gonna see the ones are gonna cancel, and then what you're gonna end up getting is, I believe is, 1/12, and it's gonna be exp to the minus quantity y minus 6 squared over 2 sigma Gaussian squared minus exp to the minus y plus 6 squared over 2 sigma Gaussian squared. But it has to have a range of the lower bound y greater than 0. Or sorry, y greater than 6. Y'all follow me on that?
No.
Because
So I first I was confused with so if x is y minus n, I thought the same thing. Why are the bounds y minus 6 to y plus 6? Wouldn't it be y plus 6 because the lower bound of n is negative 6? So that's the part that I didn't understand. Why would it not be y plus 6 to y minus 6? Other than the fact that would be integrated backwards.
well, you can just throw a minus on it.
Yeah, but you didn't do that.
Well, I think it's going to be effectively the same thing, and I'll show you why. I think that's exactly what happens. So if you think about, technically speaking, when we're doing this, we have that 1/12 right here. I'm just going to put it here. And then I'm putting an x prime there for a reason. I'll just call it sigma Gaussian squared. That's no consequence. exp to the minus x prime squared over 2 sigma Gaussian squared, and that's dx prime. Right there, and there's a lower limit and an upper limit, right?
Yep.
Now here it's an x prime, so y equals x plus noise. This is an x prime integration of y minus n. The lower limit is minus 6, and that is for x, right?
Yeah.
So here, if I put minus 6 here,
For n, right?
pardon me, n. No, it's x prime. When I'm doing this integral, hold it. This is an x prime integration, right? I'm integrating out dx, so I have to integrate over the range of x that's legit.
And is it because x is Rayleigh and it's only legit for x?
No.
greater than 0?
It doesn't matter about that. The limits you have to put on, then you have to deal with them. All right, so the lower limit, y minus 6, that actually makes sense. So if this is x prime equals y minus 6, wait a second. That should be plus 6, shouldn't it? So it should be y plus 6. And this should be y minus 6 up here. Oh, that's right. Just look, when you do this integration, look, if you think about this, when you do this, this is going to be a Rayleigh distribution. Just listen to me for a second. When I do that, with 1/12 out in front, that's sigma g squared. Then when you integrate this, you get 1 minus the x exponential. But you take the upper boundary, which is y minus 6. There it is. Right there, I've got these opposite. This should be, I believe, here, and that there. Let me do it this way. This is not making a lot of sense right now. Put a minus sign. I'm trying to get you your quiz. I've got 15 minutes. Tell you what, I'll finish this. And excuse me today. It's been This is one of the days I'm not proud of, but I'm exhausted. Let me get this to you. I'll leave that on the board. If you need anything else, go ahead. But I will do this entirely.